Hey robot makers, hope you're having a good day so far. So do you want to know how to use an RFID module with a Raspberry Pi Pico and use that in your projects? Then this is the show for you. So let's dive straight in. My name's Kevin, come with me as we build robots, bring them to life with code and have a whole load of fun along the way. So let's get over to our keynote and have a look what this is all about. So you can see on a little sneaky peek there, that's what we're going to be looking at today, which is the RFID module that we can use on some of our projects. So let's have a look at some of the goals of this session today. So we're going to be learning about the RC522 RFID module. It's quite a common module. It's quite cheap as well to purchase, as are the additional cards and key fobs and everything else that you might want to use on that particular device. So today we're going to look at how we use that module on the Raspberry Pi Pico, look at some of the code. We're going to look at what RFID is, how it works, the different types of RFID, and then specifically using this module. Okay, so what is RFID? So you might have come across this, you might not have been realizing that this is what the technology was behind the scenes. So radio frequency identification has been around for quite a while now, and it's simply a small circuit that can be attached to packages to enable tracking in transit. It can also be used for livestock tracking, payment and ticketing, fraud prevention. It can be used for door entry systems, access entry, where you sort of scan yourself in. Cashless catering, I've seen it used in schools and colleges so that students can sort of pay for things with their card. Also reprographics and photocopying. I've seen it used there. Libraries use it in books. They tend to have them on the inside cover of a book, and that can be prevent people from walking out the library with a book without checking it out first, and also to check out who's got what book. It's quite a nice quick way of identifying something, a bit like a barcode but more interactive. And also shoplift prevention. I've got my teeth in today. So quite a few shops have these things stuck on high quality items, high value items I should say, and then if they don't deactivate the tag before you leave the store, it will trigger the alert as you go through the sensors, the scanners. So it's all the same kind of technology used at different levels. So we're going to have a look at all the different levels today. So how do these RFID tags actually work? So it's a radio frequency thing. So inside this little card here, if I turn my mobile phone on and put the torch on there, let's see if I can get this to shine through. Maybe you can't quite see it on here. No, I didn't plan this bit out beforehand. I was just trying to see if you could actually see in here. So inside here, there is, just like you can see on the screen here, a little chip in the corner, and then there's also an antenna that goes all the way around the card itself as well. So what happens is you have an RFID reader or a module that can detect RFID tags, and when they come into the field of that RFID module, the power of that RF signal will actually trigger the chip that's in here to sort of wake up and send the data that it has waiting to that RFID reader. So these things can actually store more than just an identification number. They can actually store quite a bit of data. I say quite a bit, we're not talking like gigabytes of data, we're talking kilobytes, but even so, there's quite a bit that can go on in there. So when it's triggered by an electromagnetic interrogation pulse from a nearby RFID reader device, the tag transmits its digital data, usually identifying an inventory number, back to the reader. So that's the simplest form. It has a unique number on this card, which we could program if we wish, and then you can recognize what that is. So we can see on the little diagram there, the reader sends out its pulse, and the chip that's embedded within this card, the antenna, receives that signal, powers the chip, and the chip responds back through that same antenna to say, I'm card number 123. So there are different frequencies, different bands involved in these cards. So this technology has matured over quite a while. So there's low frequency, high frequency, and ultra high frequency. Typically the low frequency is between 30 kilohertz and 300 kilohertz. And the typical uses for that are livestock tracking, door entry systems, and they use specifically the 125 kilohertz or 134 kilohertz frequencies. And then in the high frequency, which is what this card is here, that's between 3 megahertz and 30 megahertz. And specifically, this card uses 13.56 megahertz. And these are for ticketing, payment, again, data transfer, I thought I said door entry, data transfer. And then the ultra high frequency, which is between 300 megahertz and 3 gigahertz, that's used for things like inventory management, pharmaceutical, anti-counterfeiting. That's a bizarre one. They actually attach these things to, say you want a sample and you want to make sure that sample has got a chain of custody all the way from where it was taken all the way to where it's being processed. So say it was like pharmaceutical or even law enforcement, you can use tags to ensure that. And also wireless device configuration. So if you have a mobile phone and you have a new mobile phone and you want to sort of pair the two together and transfer the data between them, or send Wi-Fi access point details, you use this same kind of technology. So it's very high frequency, which means you can send a lot of data very quickly, but you do need to be closer. So low frequency, they can be quite a considerable distance away, maybe 10 centimeters away from the actual reader, and then the high frequency ones, you get that bit closer again, and then ultra high, you almost have to be touching for that to work. And then RFID tag anatomy. So let's have a look at how this thing works. So in the very middle of the chip, of the tag is a little chip, and then spiraling out from that, and the distance that it spirals round is very precise. That gives it the frequency that it's tuned to. So there's an RFID chip and then there's an antenna, and these things are extremely thin, so you wouldn't even know if you have one, say inside of a book cover. It wouldn't take up more than a page, so it's really, really thin. We're just talking the sheet of paper kind of thinness. And that's why they can be embedded in these sort of very thin credit card sized things, or the more robust key fob ones. But that's quite a thick piece of plastic there. So very simple. The different types, so as I've just been showing there, I have two here. I've got the blue key fob. So the idea is you would have that on your keychain, and it's designed to be quite robust. So the plastic that it's got around it is very, very hard. So you can put that through the washing machine, you can stand on it and all kinds of stuff, and it will probably survive. The key fob one is designed to be, either in a lanyard around your neck or in your wallet, and it's very thin, so you can keep that about your person. But they all work in exactly the same way. So the same chip just has a different size antenna. And then the one at the top right of the diagram there is the sticker, the RFID sticker tag, and those are the ones that you'll find on packaging. So if you get this box has got one here that I think this is just barcodes. But yes, if you have sometimes library books, packages, other things, high value goods from a supermarket, they tend to have these sticker ones on. Again, that wiggly line is the antenna, and the bit in the very middle of that bit there is the actual chip. So it doesn't require any kind of battery, any kind of external power. The power of the wave coming over, coming into effect, powers the chip and enables it to send out back the data that's in there. So lots of use cases, as Darren says there in chat, for RFID. So if you like these videos, please make sure you like, comment and subscribe. So drop me a like if you're watching this on Facebook or on YouTube. Drop me a comment what you think. Have you used these before? Have you got any ideas how you could use these in your projects? So what I'm thinking for myself, for my projects, is I'm going to have one of these SMARS robots, and then on the top we'll have the RFID reader. So very, very thin thing. We can easily put that on top of the robot, and then we could have different cards that do different things. If you do that, it might make the robot go into object avoid mode. Another card you put on top might make it go into follow mode, and so on. So we could use these quite simply to program, or at least select the program. I have seen some innovative uses of the cards where each card has a different programming function, like an if statement, and you build up an entire deck of these, and then you have to present each one to the card reader to build up your program. A bit tedious that, but I guess if you're doing sort of introductory level stuff, that could be of use. So yes, if you like that, drop me a comment, let me know what you think you're going to use it for, and if you've not already subscribed to the channel, consider doing that if it's something that's of value to you. I do go live every single Sunday at 7 o'clock Greenwich Mean Time-ish, depends if we're in British summertime or not, but we are in now GMT, so if you're watching this, it's the normal time zone. Okay, and you of course can follow me on social media. So Alex has popped some links in the chat as well. If you're watching the chat, you can follow me on all those various different social media. So Twitter, Facebook, obviously on YouTube. I'm on smarsfan.com as well, email and also Instagram. So if you go to that link there, smarsfan.com/about/link_in_bio, you can check out all the different links there and follow me. Okay, let's get back to this. So this specifically, the RFID522 module. So I bought a bunch of these. I bought a 3-pack of these, so I've actually got quite a few of them. And I'm also thinking about buying a couple more cards. They're not that expensive. They can be between 5 and 50p per card, depending how many buy. So I might buy a deck of them and put some kind of sticky label on one side to show what it is. So very easy to come by. The header pins are 3.3 volts, so they work very nicely with the Raspberry Pi Pico, which is 3.3 volts. It uses the SPI or SPI interface, so at the very top of the board there, I just hold this up and go into full screen mode for a second. You can see there's a whole bunch of header things there, and we actually read it that way round. You can see there we've got the data, we've got the clock, we've got the MOSI, we've got the MISO, so that's output and input. There's an IRQ, there's a ground, there's a reset, and there is a 3.3 volts. So very, very simple. It's quite a thin device as well. And I'll show you, I've actually printed out a module. I'll show you this in a minute to sort of encase this, so we can have a nice little 3D printed enclosure, so that we can then come along and just put our card against the scanner part. It just has a little bit of a head thing there because of that crystal chip. That looks very familiar, that crystal chip. Anybody that's looked at Arduinos, we recognise that as being a crystal. Okay, we'll just put that back over there. Okay, so what else? It doesn't use very much power. We can see there the power rating. So at peak, it's less than 30 milliamps, is that? Operating frequency, which we talked about earlier, is 13.56 megahertz for this particular module. So if you want to use different types of cards, you will have to have a card reader that is tuned or is compatible with the types of reader that you have. So readers and cards can come in pairs, if you like. So the supported card types for this particular one is the, to pronounce this, MFRC one S50, the S70 and the Ultralight. So this card I think is an S50 if I'm not mistaken. And it says the data transfer rate, the maximum is 100 megabits, which is quite a bit. Sorry, 10 megabits, which is quite a bit. And weight-wise, it's 21 grams. It weighs practically nothing. It's very, very lightweight. Okay, so the types of card and standards. So there are different types of card. There are 8-bit and 10-bit cards. There are 1 4K or 8K cards, and that refers to how much memory is stored or is available to you on the actual card. There's mini, there's MyFair 1K, MyFair 4K, and so on. So these cards, I think, are 1K cards. We can have a look at that in a minute when we interrogate it, and we can see how much memory it has there. And as with all these things, I always think, oh, I'll just buy one of those modules and then I'll do a video on it. How hard can it be? It's pretty simple to get these things working, but as you can see there from the standards thing, there's a lot of reading to be done. This is a bit of a rabbit hole if you start to want to do things that are really fancy with it. So we'll get into the kind of fancy things you can do with these cards. But if you just want to read a unique value or write a unique value to the cards, that's pretty trivial. However, you want to do all these other things with it, you then need to start looking at the libraries and all the different standards that come with this. It's standardized because it's used in industry and they need to make sure these things are compatible. Okay, so how do we wire this thing up? It's pretty simple. If you've ever done any SPI wiring before, it's pretty straightforward. So we have voltage and ground. We have a system data and system clock, which is the first two over here. Then we've got the output and input. IRQ is used if you want to receive a signal to say that the card reader has been activated, and then you can deal with the request. We're not using that on this one, so you can actually leave that pin off. Yeah, we said we've got the ground and the voltage, and then there's a reset as well, which just resets the card reader if we ping that value. So like I said, we don't need to use the IRQ pin. Pretty straightforward. And then to the Raspberry Pi Pico, so I've got the reset to ground to pin 0. The data is on pin 1. With the clock is on pin 2, the output is on pin 3, and the input is on pin 4. So they conveniently are all right next to each other on the Raspberry Pi Pico. So if I'm looking at this correctly, pin 0 is the very top one, pin 1 is the next one down, then there's a ground, then you've got 2, 3 and 4 next to each other. So works pretty easily. So yes, these cards can be used to store some data on them. So what kind of data would we want to store on these things? We'll have a look at that in a minute. But the memory itself isn't that straightforward. Because this has been an evolving standard, there's a few different types of memory that we need to be aware of. So there's reserved memory. So these were designed for things like door entry systems. So because of that, there is a kill password, which will permanently disable the card, as well as the access password. And each of them are a 32-bit number. And the idea is if you want to deactivate this card, you also have to know the access password. So the program that's interrogating this will have to know one or the other to be able to deactivate or even use the card. So if we want to write to some of the memory areas, we also have to have that permission. We have to have that access code. Then there's the electronic product code number. So the EPC memory is simply just a 96-bit code that we can use, and that's the ID itself. That's what we most commonly use for the ID. There is another area of memory which is the TID, the tag ID. This is typically a read-only piece of memory. So if you create one of these stickers, you might program into the memory, so there's no way to change this, so it's quite secure, a unique number. So it doesn't say how many bytes that is when I was doing my research on that. And then the next bit is the user memory. This is where we can read and write all our own stuff too. So there's up to 8K of RAM. Takes a little couple of seconds to write that much. We'll see that when we have a look at the code in a second. But it's quite usable. We can put things in there. So what kind of things we want to put in there? So there's a standard for that, of course. There's this NDEF format. So this is the, if you've heard of NFC, so when you go to the supermarket or you're purchasing a good and you've got your phone and you can sort of pay with your phone or with your Apple Watch, they're using this near field communication NFC protocol. And there is a near field communication data exchange format. And that's what this NDEF is all about. It's the near field communication data exchange format. So it's a very long-winded way of saying it's a template, it's a format that we need to be aware of. So if we want to use that, we just have to have, we have to know what headers, how many bytes are in each section, and what we can use them for. So there's two things there. There is an NDEF message and an NDEF record. The class provides methods to retrieve and modify the NDEF message on a tag, and this is from the source code that I'm going to be looking at in a minute. And there are currently 4 different NFC forum standard tags that we can use to contain specific types of data. If you want to know more about these, go to the Adafruit Learning System. They've got a really great resource on this. So check out that link there. So learn.adafruit.com/Adafruit-PN532, which I think is their model for the reader, -RFID-NFC/NDEF. And you'll be able to learn a bit more about that. So why would you want to know about this data format? What can we use with that? So what we can store on here is things like a URL. So if we wanted to make it so that when somebody puts this against their phone, it pops up with here's a website address. A bit like with a QR code when you can scan it and you'll get like the URL. It's exactly like that. It's a format for standardizing things, and the device that's reading it will know what that data means. It's not just a useless piece of text. It can interpret it. So there's lots of different types of link that you can put in there, the usual kind of internet ones. So let's have a look at some code, shall we? And then we can have a play. So let me just break out a second and bring up Visual Studio. Let me just move that over there, and then I can get my screen ready. Okay, so I've got a couple of programs, and this source code is available if you want to download this and have a play with it yourself. I've made it quite straightforward. I've even put the STL files for the card reader, which I've got over here. So I've got my little card reader. This is the one we're going to be looking at today. So I've just got a Raspberry Pi Pico that's been wired up, and we've got the card reader there. So there's a little base piece, and then there's the lid that kind of goes on the top of it, and it just kind of clicks into place like so. So we can present a card to this and so on. Okay, let me just stop my code from running because it's gonna spoil it all. So can I do clear on that? Let's just do that. Let's go back to the code. Okay, So I've got a couple of programs on here, and there's a couple of libraries too. So we're going to be looking at the NDEF read for now, and then we're going to be looking at the arrays, the create, and we'll have a look at some of the lower level libraries as well. So let's have a look at the NDEF read for now. Let me scroll the code to the very top. So what we're going to do is we're going to bring in from the library the MFRC522. We're going to import the class that represents that hardware. We're going to import uTime as well, which is just the Python, MicroPython time module. You can actually just do time, to be honest, like that, but we'll bring in uTime. We then create a reader variable which comes from that class, and then we have to populate all the different pins for the SPI. So we pass in the SPI ID of 0, the system clock is pin 2, the MISO is 4, the input, the output is on 3, the chip select, which is also the data SDA, is on pin 1, and the reset is pin 0. And then we print a blank line, print the text, place card into reader, and then print another blank line. We then have a variable that's called previous card, and we just make that equal to 0. We make that array equal to 0. And then we try to do something, and if we just look, if I just collapse down that try block there, you can see that the except piece, so it'll keep going round except if we press the Control C, so the keyboard interrupt, otherwise it'll just say bye. Okay, so while true, we're going to initialize the reader. We're then going to take some requests from the reader. We're going to look at the stats and the tag type. If the stats reader is okay, so there's no errors, then it'll continue to the next bit. So we get the stats and the unique ID from the reader, and it's going to read the tag. And then if the unique ID is the same as the previous card, then basically just continue, jump past this block of code is what that means. And that's to stop it from, if we put the card on the reader, and it reads and reads and reads and reads and reads, we'll just get loads of things scrolling up the screen, and we really want to just read it once. So that's what that prevents from happening. And then if the stat equals reader okay, so if everything looks great for now, then we can say card detected, the unique ID is blah, and then we can pass in from that what the unique ID was and what the reader 2-hex string unique ID is, and that just sort of unpacks it, decodes it. It's quite a complicated looking line there, but we can read through and understand what's going on. So we're using a print statement. When you print out text, you can format text, and you can say hex is a function that will take in a number and represent it in hexadecimal form. Int is an integer, it's a whole number, so we're casting the value, which is the hex number, into an integer. And then from the bytes that we're reading in, and the bytes is a packed array of numbers, we're bringing in that unique ID. And the little is the in 2's complement. So when you're looking at numbers in binary, because you can copyright formats of things, when it wasn't Intel, it was the other company, Motorola, they copyrighted the format of a binary number. So when you look at a number, a binary number, and you start from, like, you know, the first bit is it a 1 or is it not? The next one, is it a 2 or not? And so on. If you just put all that out into infinity, I think that's called little endian. Little endian, meaning the end of the number is little. If you have big endian, that's the Intel format. Now, correct me if I'm wrong, people in the chat, if you know that that's correct or not, but essentially you have to sort of take that first block of numbers and then shove that onto the end, and that's like big endian. And the reason they do that is just because of a copyright issue between, like, Motorola and Intel back in the day. And what little means is it's the little format that we're looking at for these numbers. If you don't do that, the number is completely wrong. So it's one of those pieces of mad trivia that you need to know when you're working with binary. Okay, so then there's different sectors. So remember we were talking about the 4 different types of memory. So these sectors are the areas of memory. So we're going to read in the first key, which is just these blocks here. Then we're going to read in the next sector key, and there's a default key, which is just all the 255, so just like the highest number that we can have there. And then if the reader dump classic 1k function returns OK, then we can carry on with the rest of the card. We can read all the memory in from that, and it'll just keep reading in, keep dumping out to the screen all those different things. Once it's finished, it'll print done, and then the previous card will equal the current ID. And then otherwise, we can go back up there. So if the stat reader is okay, if it's not okay, then the previous card equals 0. So we just wipe that. And then we wait for 15 milliseconds. So quite a bit going on there. Not a long piece of code, but quite fiddly. Lots of low-level stuff going on there. These 0-X, that's a way of writing hexadecimal numbers. So the 0x means that it's a hexadecimal. So it means it's a value between 0 and 16. And that's quite a messy thing to look at when you're looking at code. I always try and convert it to something that's a lot more plain English, like that one, 255. We can understand that is a normal base 10 number. If we had 0FF, that would be the same as 255. It would be 2 bytes, and that represents the highest value that we can have with 8 bits. Okay, so that's the code. Let's run this code, shall we? I'll head over to my split screen. I just need to change my bench cam to be the right camera. So this needs to be the overhead. Is it that one? There we go. So what I'm going to do, I'm just going to position Visual Studio a bit better so that we can see what's going on. And I just need to shrink everything down a bit so we can get it all on the same page. Right, there we go. That'll do. Okay, so I'm going to run the code by clicking on the... So I've got Visual Studio Code. I've got the Pico Go module installed, and Pico Go gives me this nice run button here. So we've got the text there. It says place the card into the reader, which we've seen before. Let me just click on that. There we go. So if I get a card that I've just got lying around here and I just place this over the reader, it says authentication error. So I'm going to try a different card. Let's try this one instead, and I'll hold this one over, and you can see there we've got loads of data. So we've got 63 lines of data, and there are different banks. There is 4 banks, B0, B1, B2, B3, and then there's different slots. There's 16 different slots of memory. And if I scroll back up, we can see at the very top there, there's some data in there. Not very much data, but we can see that there is something in there. Now the reason the other card said authentication error is because that number that we had coded into the code for the access password and the access code were not the same what's on the card. So it kind of says, nope, you're not allowed to read this. This didn't match. So it's kind of a protection thing. So it'll only return back the values if the password and the access code that you give it are the ones that are stored on the card. So there's no way to interrogate it without having the correct one. So it's quite secure. So we can actually erase this card, the bad card, by going to our next piece of code, which is the erase code. So let's just go back to our Visual Studio and have a look at this. Okay, so let's just scroll that down a little bit. So we've got the similar kind of thing that we had before. We've got the reader, but this time we've got access, which is coming in from a different library, the RFID access library, and we're bringing in the access code. We'll have a look at this library in a moment or two. So then we've got a couple of lines. Please place the card on the reader. We're doing the previous card thing again. We're initializing the thing. So these are all the similar that we've done before. The difference is here, the access code, we are going to decode the access using these 3 bytes. And then the block 3 access fill block, we're going to fill that with a code that we've chosen. So this is a code that we've decided to create. It's going to reset the MAD sector, the first sector. It's going to write that. We can see the reader.write sector. And then we're going to, after that's been successful, we're then going to do the data block 16 times 0. Remember there are 16 different banks that we have with 4 different, what would you call them? The 16 banks, 4 banks with 16 slots. I think that's how you do it. Yeah, so S in the range 1 to 16, so sectors, that's the word I was looking for. They're going to just wipe that with stuff. Once that's finished, we can then say card done. So let's run this code. Let's get back over to here. Let me just move that down again so we can see everything on one page. Let's get it to about there. And then let's just bring up this a little bit. Okay, so I'm going to stop that. I'm now going to run this code. So, oops. So it's complaining that it can't find RFID access. So I'm just going to upload that to the Pico. Let's just upload that code. Done, and then we can run that again. Okay, so just scrolling up to see what it's trying to do. I'm going to put the card on the reader and then I'm going to run the code. Let's see if that works. That doesn't look like that's running to me properly. Let me see what's going on. X decode bits, show access. Let's try running the other one now. Did I click on the right one there? Let me just go back to erase and then run. There we go, that looks better. It should say place the card on the reader, but it's complaining about that again. RFID access is on there, and the reason is because I changed the file name to be lowercase, so that's why it's complaining. So let's just change that code, and then let's run this again. There definitely is a piece of code called RFID access. Let's just upload that again. It's not accepted that that's been changed. Okay, let me disconnect this from here. I'm just going to use Thonny because Thonny is a lot easier to erase files. So let's just throw up Thonny for a second. What I need to do, there's a file on there that's got the same name, but some of the characters are in uppercase. And on the Raspberry Pi Pico, it isn't case sensitive in that sense. So that means that it won't actually understand. Did Thonny not load then? It won't actually understand that the file has changed. So I just need to quickly delete the old file. Let's go to here. So we want to be on Raspberry Pi Pico. And we just want to erase, see that file there, RFID access. I want that to be deleted, and we want to upload the other one. So let's just delete that. Yes. I can come back out of Thonny now, back over to Visual Studio. We can connect again, and now we can upload that code. So let's just try that. And let's try running our code once more. So we're on the erase one. So let's run that. It's still complaining about that. RFID access. RFID access. .py. That's frustrating. This worked when I tried this out before. I did rename it, but everything else should be the same in there. Let me just have a quick look. Let's go back full screen on this and have a look through the code. Just make sure there's no errors that are being reported. So no, that looks good. So what I'll do, I'll actually upload this code. Sometimes it does that. Let's try running this now. Line 2, no module called RFID access. RFID access. So I think that's still the same actually. That was my mistake there. I've only renamed the file and not the class. Let's try that. Boom, come on, let's work. It's taken a very long time. Normally when there's an error, it takes a long time and then reports the error rather than just reporting it right away. I think this should work this time though. So I'm just going to stop that, reset the card. Sometimes Visual Studio has a bit of a moment as well. So let's just restart that. The joys of live streaming and code. Right, let me just load that back up again. What I want to show you is that this card that we had before said access denied, and that's because it has a number on it. We don't know what that is. We want to erase that and we want to make it work with our new number that we've decided, which is those 3 bytes that we looked at before. Okay, Visual Studio is now coming back up. We're on the erase code. I've got the Pico plugged in. I can see that we have that. It's got a light showing there, which is good. Okay, Yes, Alex has got a cold at the moment. She's doing her really best to not cough. It's fine. Okay, so let's now go to... Just waiting for it to restart and have the little Pico Go thing at the bottom. But because we're live streaming, it's taking quite a bit of my resources in my machine, so it's a little bit sluggish. There we go. So once that appears there, we can press run and we can try this code out. Okay, we don't need the Jupyter extensions, we just want Pico Go. There we go. Let's run that now. Okay. So it should just come down here and just say, please place card on reader. I don't know why that's not working. That really should work. How bizarre. I'm just going to give it another couple of seconds to time out. Otherwise, let's just have a look through our code. Let's have a look through that file itself and see what's going on. So RFID access. So the R is capitalized, the A is capitalized. So we've got in our code the R is capitalized, the A is capitalized, R and A. So that all looks good. So the read one works. Let's just run that one instead. And now it's saying that the Pico is not connected. Right, let's just have a look at, let's just do Control D. Yep, so we're on quite a new version of the Raspberry Pi Pico software. Let's just try the read one again. Okay, we're going to run this code. So that one says place card on reader. So that's the good card. Let's try the bad card. So that says authentication error. So that is the bad card just there. Good one is there. So now let's stop that and then try the other one again one last time. So it still can't find that RFID access, which is just really weird. So when I say writing the file, it's still writing the old one with the uppercase name. Okay, let's go back to Thonny and remove that file and open up this in Thonny instead. Maybe that's the right way to get this working. Okay, let's let Thonny load up. Okay, and let's just go full screen on this for a second. So let's open up this this program. So it's in my MicroPython folder and it's Pico RFID, and it's the erase program that we're looking for. Excuse me. And once that refreshes this list here, so do we need to do that on here? We need to let's try that again. We need to open up this folder. So let's just go back there. Let's go into Raspberry Pi Pico RFID. There we go. There's our RFID. Let's just toggle that. And let's erase that one. And then let's upload it. It's as if it's cached the file for some reason. Let's upload that. Now we should be able to run erase. So let's run that. There we go. So the bad card is this one I've got over here. So let's place that on the card reader. Card detected, and reset to the mad sector, the first sector, and then it's resetting each of the sectors one at a time. So it takes a little bit of time for it to do that. There are 16 different sectors that it's got to write to. So it's just got 5 more to go. And then we'll try running that read program and see if we get the authentication denied. So it says authentication error at the bottom, but let's just try running the read error now, the read program. So let's run that, place this onto the reader, and we're still getting the authentication error, whereas the other card still works, does it? No, that one's getting, there we go, that one's still working fine. So let's just run this on here again. Now there's another package here. I've not actually opened this one yet. I'm going to open this one up and see what this one has on it. And this is kind of as they come out the package. And then we'll try one of the fobs as well. So they come with all the different parts. There's a fob and then there's the card. It's the card I'm interested in. So let's now try putting this card over and see what happens. That one says the same thing. It's got the exact same unique ID as well, which is interesting. I thought they would all be unique. So if we put that one on there, that one's bad. Oh, it does have a different number. You can see the different numbers. That is a different number to that there. Let's try this one. That one says authentication error, and then this one reads okay. So clearly when I've been erasing them, this one is fine. So what I'm going to do, I'm going to run the create one this time. Let's open the create module. Let's just change the case of that one file. You can't quite see what I'm doing there, so let's just go full screen a second. So this is the create. This is going to create a new ndef tag. And this one has got some ugly code in it. So there's a checksum. This cyclic redundancy check has got a number. It's going to basically just check all the data that comes in equals what does that mean? Up equals the byte for something in the range of 8, and it's going to go around and it's going to check if that is less than 1 and nothing. So, and then more significant bit should be equal to that. So that's a cyclic redundancy check. I'd have to look through that code a bit further just to understand what this little piece is doing here. I think that's a bit shifter that shifts it by 2 bytes, but I'm not sure, by 2 bits or by a single bit. And the rest of the code is very similar to what we've looked at before. So it's going to detect the card, it's going to look at all the different sectors, and then it's going to access the sectors, the trailer access, the block access. And this is where when I was talking about those ISO standards, this can get quite ugly if you're not familiar with these. I just want to be able to plug and play and make the thing work. So let's just try stopping that code and running this create tag. So it should say place card on the reader. So I'm going to do that. So it's written the first. Let's try that again. Let's try with the different card. And then let's try with the third card. So that's our good card that works. So clearly I've done something with this one card that works well and the rest of them it doesn't like. So let's try reading now with this key fob. So if I go to the key fob, read, let's stop that code and run this code. And I'm going to place this fob onto the reader. We can see there that it's got a whole bunch of data, and this has also got 1K of data. So if we times 63 by the number of bytes that are on there, so we've got 1, 2, 3, let's just count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14, 15, 16. So 63 times 16, that's probably our 1 byte, isn't it? 63 times 16. Yep, that's 1008. So that's our 1K. So that was one fob. Let's try another fob. Let's try putting this one on here. So that one says authentication error. Interesting. Let's try the third fob that I have. Let's see what that says. So only one of these is currently authorized, which is that one there. If you take it away while it's reading, obviously it can't read all the data that's in there. But if you leave it on there, obviously it can read through. And we can see there's nothing else there. There's just a tiny bit of data at the very top. So if I want to play around with this a bit more, I'll probably do a midweek video on how to get these working in kind of every case. But what's going on there is the data that's in that very first chunk of memory, which is the unique access code for that card, and the ID of that card. If that doesn't match what you're presenting to it to say wipe this card, it will just ignore it. Or if you're saying overwrite what's in this or read from this without providing the correct code, it will not let you do that. So these 3 functions should let you create those ndef records. Now there are some other pieces of code. I think I'll probably remove them from here. And they are the things that allow you to override what's in there and just wipe the card proper. So let's have a look at the MFRC522 library. So I'm going to go full screen on this one, and let's have a look what's going on in this piece of code. So the first thing we import is machine, pin and SPI. So that's obviously to connect to our Raspberry Pi Pico, and we're also importing uname, which is this sort of the details of the version of Python that you're using on there, because it's an operating system thing. We then create this class, this MFRC522 class. We set debug to false, we set OK to 0, and we set a whole bunch of other things to some very specific values. We then do an initialization thing, so there's a baud rate there. We can see what that is, because this is sending serial data between a device or a reader. So that's the reader being the module, and the baud rate between the Raspberry Pi Pico over the SPI and the device. We've then got all the SPI pins, so that's what all these clock, output, input, reset and data pins are all about. The reset and the chip select are also got values there. The type of outputs and inputs are specified there as well, so that MicroPython knows whether it's data coming in or data going out. And then they've got some specific things on here. So if the board is a YPi, low Pi or a Phi Pi, which is a different type of, instead of it being a Raspberry Pi Pico, it's a different board. Or if it's an ESP826 or an ESP32, just going to change the baud rate. You can see there that's got a million, that's got 100,000. Otherwise, if it's an RP2, which is the Raspberry Pi 2, then use the baud rate specified above. Otherwise, say this is an unsupported platform. We then reset the module by sending the reset value 1. We initialize this function, and then we've got some other functions as well. So that underscore means that it's hidden from the user when they're trying to do like autocomplete. If you've got the underscore in front of it, it hides that function. So these are some really low level functions. So reg, I would hazard a guess that that's write to a register. So we pass in the register and the value, and it will do an SPI write to that particular register. Reg, I assume, would be a read from the register. We've then got some set flags, set and get of flags. We've got something to the card. And what else have we got further down here? We've got the cyclic redundancy check that we looked at before. There's an init, which basically just sends some default values to everything. And these write registers will tell the device to ready itself. We've got the reset, which just sends a 1 and an F to the to register 1, sends an F to that. Antenna on request. What else have we got? Anti-call, no idea what that is. Then we've got PCD select, select tag, and then 2 hex string. And then the select the tag, we've got, just looking through the header names, we've got authenticate keys, we've got stop crypto, read, write sector block, read sector block. And then we've got dump classic, which is that thing that we saw before where all the different lines, that bit below there, that's the dump classic thing. And that's it. So there's quite a lot in there, not very friendly library. This isn't one I've written. You can see there the author is Dan Perron on GitHub. So if you go over to Dan J. Perron and look at the MicroPython-MFRC522, you'll be able to find his code there. And I've basically taken that verbatim and put it in here. So I'm not claiming to have written anything there. So what I'm looking to do is basically just wrap that into a bit more of a user-friendly library. Okay, so that's me waffling on a little bit. Let's have a look at what some people have been saying in the chat. I can see you've been busily talking about stuff there, so let's have a scroll right back to the top. And we can see. So at this point in the video, I'm actually going to cut this off the recorded video now. So if you're watching this on playback on YouTube, I'll say bye for now. But for the people who are in the chat watching this live, we'll continue our question and answer section. So thanks for watching if you're watching this on the replay, and I shall see you next time.